So the title of my talk is Assessing and Modifying Emotion Recognition, and the core aspect that I'll focus on is this idea that social cognition lies at the heart of our social interactions. And social cognition is the ability to essentially decode what other people are thinking and their emotional states from non-verbal and verbal cues, and in particular facial expressions, which is one of the primary channels of communication between humans. And we've known for even longer than CANTAB has been around that there are primary universal emotional expressions: happiness, sadness, disgust, and so on, and that these are largely cross-cultural. So the work of Ekman in the 50s and 60s, for example, showed that Papua New Guinean tribesmen who had little contact with Western civilization could both decode emotional expressions from American university undergraduates and vice versa. So we know that there are universal emotional expressions. There's some debate around the nuance of that, but largely that is agreed. And the question is, how best can we assess that, and what role does it play in mental health disorders? What we do know is that the ability to decode emotional expressions in others is impaired across a range of different psychiatric conditions. So, for example, in depression, we see this general deficit in emotion recognition. This is a study by Michael DeLilly published earlier this year. He's a PhD student of mine, with the possible finding here that there may be a sparing of our ability to recognize sadness, if you like, in people with depression versus controls. But generally you see a deficit in the ability to recognize emotions, and also biases in how ambiguous emotions are decoded across a range of different conditions, including depression, schizophrenia, but also substance use, autism spectrum disorder, and so on. And there are interesting questions of causality there. To what extent do these biases and deficits in emotion recognition predispose to those conditions, and to what extent do those conditions lead to biases and deficits in emotion recognition? And of course, those two possibilities aren't mutually exclusive. And understanding that direction of causality and whether or not causality is operating there is obviously critical if we're going to be able to develop, in particular, cognitive behavioural treatments that may target these biases and deficits. So there's an extensive literature that attempts to assess emotion recognition, and much of that uses stimuli that were developed around the time that Ekman was doing his seminal research in the 1950s and 60s. And so these are the classic Ekman faces, which I'm sure many of you are familiar with. But obviously the world has moved on since the haircuts of the 50s and 60s, and so these faces are pretty idiosyncratic now. There are also some other features of these faces that are problematic. As well as having these idiosyncratic individual characteristics like hairstyles and eyebrows and so on, there's also an almost perfect confound between age and sex here, in that the male faces were of the PIs, the faculty if you like, and the female faces were of the RAs and the postdocs. Because then, as now, there was a systematic difference in the proportion of males and females at those different levels of academia, if you like. So there are a variety of features of these stimuli that are still widely used today that are perhaps less than ideal. So one of the things that we've done over the last few years in Bristol, together with my colleague Ian Penton-Vogue, who unfortunately can't be here today, is to develop new stimuli that address some of these limitations. And the way in which we've done that principally is by creating composite faces that are averages of a number of different photographs of volunteers expressing different emotional expressions, which removes many of those idiosyncratic features and creates prototypical faces that look like this. And using modern computer graphic techniques, we can create stimuli that look pretty naturalistic. You wouldn't necessarily immediately think that these were computer-generated composites. And we can create them for different sexes, ethnicities, age groups. And these stimuli retain the key prototypical features of the different emotions that are being expressed in the absence of these different idiosyncrasies that we see in some of these older face sets, and in the absence of some of these confounding features that may themselves be problematic. Another limitation of existing attempts or efforts to assess emotion recognition is that the comparator, particularly for bias tasks, has often been a neutral expression. And there's ongoing debate around the extent to which a neutral expression is actually emotion-free. So the mere absence of emotion is not the same as someone staring at you with a completely blank face. And certainly for people with high levels of anxiety, for example, someone staring at you with a completely blank face is actually quite threatening. So the way that we've addressed that is by creating this face space where around the outside of this hub and spoke we have the 6 primary emotions for each of the different stimulus sets that we've developed. And the neutral face in the middle is not the composite of someone just staring blankly at the camera, but rather an equal blend of all 6 emotions, so that rather than looking threatening, this is simply the balance of all of these different emotions, and therefore, in that sense, emotion neutral, because the different emotions sort of pull against each other and cancel out. And so this is just a more principled way of creating a face space within which we can look for individual differences in the ability to recognize these different emotions out along these different spokes. And that then allows us to look for individual differences in the ability to recognize those emotions, using a 6 alternative forced choice task where people are presented with a series of stimuli that range in intensity along these different spokes, with those stimuli being interleaved. And the degree of accuracy as you go out along these spokes can be assessed, and therefore individual differences in the ability to recognize emotions characterized. And so when we run this on a typical sample, an unselected sample of about 250 individuals, using 180 trials, measuring simply the ability to accurately recognize those emotions along those spokes of that hub and spoke model, with no time pressure to do so, and look at correlations with PHQ score, we get results that are very similar to that which we see in that meta-analysis of patients versus controls on a variety of different emotion recognition tasks that I showed you previously, but with a sample size considerably less than would be indicated by the effect sizes indicated by that meta-analysis, suggesting that this may be a more sensitive task for the reasons that I've talked about, principally in terms of how the stimuli have been developed. So that allows us to assess individual differences in emotion recognition across a range of conditions, but what we may be more interested in going forward is the ability to modify those biases and deficits, first with a view to understanding whether these relationships are causal, and if so, in what direction, and secondly, with a view to developing novel therapeutic interventions that may complement existing CBT techniques or pharmacological interventions. So the idea here is that one of the mechanisms through which these biases and deficits may impact on social interactions and thereby mental health is that if we have a bias in our recognition of this or our interpretation of this ambiguous expression, such as that we see this as essentially hostile, then of course we will respond accordingly to what we think we're seeing, and you will establish this vicious cycle driven by that bias in the recognition of an ambiguous expression. And if we can break that cycle so that this person sees the same stimulus as either not hostile or in fact positive, then of course you're going to establish a virtuous cycle and help people break out of that vicious cycle. So can we do that? Well, we've developed a task that does that using the same kind of stimuli. We can take the same stimulus sets and create ambiguous expressions that morph not from this neutral center point that we have out to the full emotion, but from one full emotion to another full emotion, so that the mid-range is ambiguous. Present people with what are these stimuli, with a pattern mask to prevent after effects, and then ask people to simply judge whether the face is, say, happy or angry or happy or sad, depending on the stimulus set that's being used. And this is self-paced, and we can do that in order to establish that individual's threshold, the point at which they stop seeing one emotion and start seeing another emotion. And recognition of these ambiguous expressions tends to follow a sigmoidal function. It's a step function. You see happy faces, and then you stop seeing happy faces, and you start seeing angry faces on this 2 alternative forced choice task. So you you measure that person's baseline threshold, then you take that baseline threshold, and in the intervention condition, in the training condition, you provide feedback that is designed to shift people along that sequence, so that the 2 faces to the right of that threshold that I just showed you, that previously would have been described as angry more than 50% of the time by that participant, we say with simple feedback, no, that's not angry, that's happy. So when they respond to those faces as angry, which they would have done based on their initial threshold, we say that's incorrect, that face in fact is happy. And in the control condition, we give feedback that is intended simply to keep their threshold at the same point. And so what we do is then shift people or shift people's threshold 1 or 2 steps along this sequence. This is a shortened sequence. The real sequence that we would use would be at least 15 stimuli long. And we can do this either for ambiguous expressions, so this is a sequence that ranges from happy to angry, or we can use it to change sensitivity. So this is a sequence that ranges from not happy to happy, and this not happy face is what happens when we morph through that center point of that hub and spoke model that I showed you previously out the other side, if you like, so that you are not going from happiness to sadness, but from happiness to anti-happiness, if you like. And you can use that to increase sensitivity to a specific emotion. So you have 2 variants of the task, one of which can target ambiguity and biases in the recognition of those ambiguous expressions, and one that targets sensitivity and our ability to pick up specific emotions. One question, of course, is, since that we're using these prototypical faces, is do those effects generalize? If we present a new stimulus set, do we see the same training effects as we see when the stimulus set remains constant from the baseline through to the test phases? So we tested that in 160 healthy volunteers, and again, this was part of Michael DeLilly's PhD work, where people are trained on one stimulus set and then tested on the same stimulus set after training. And we had 2 stimulus sets that we used here, or they were trained on one stimulus set and then tested on a different stimulus set. Now, what we understand about how emotions are encoded would suggest that the training effects should be identical, because these effects should generalize, because what's being trained is the genuine recognition of that emotion, if you like, at a prototypical level. And when we see the magnitude of the training effects in both the congruent conditions and the incongruent conditions, we can see that the magnitude of those training effects is exactly the same. So the argument here is that not only can we train people to recognize one emotion over another, or to be more sensitive to a particular emotion, but that training will then generalize to other faces that weren't part of that training. So this is what the behavioral data look like in the intervention group compared to the training group, where people are given a 20-minute training session once a day over the course of 5 days. And you can see that from pre-training to post-training, we see this shift in threshold. It falls back slightly the next day, but not back to the starting point, if you like. So some of that training effect is carried out into the world for 24 hours and generalizes to other emotional expressions. And the extent to which you can shift that training reduces over time, because, of course, there comes a point where you simply can't convince people that that's a happy face, because it's obviously not. And then we have the control condition down here. So we can induce a 2-frame shift very easily and strengthen that over the course of 5 days. And we've shown that this training effect is still detectable 6 weeks after this course of 5-day training. And critically, when we then put people into an fMRI magnet and look at their responding to happy faces and sad faces, for example, what we see is that for this training, which was on a happy to sad sequence, training people to see more happiness in ambiguous expressions, if you like, which might be a target for intervention in depression, we see an increased response to happy faces relative to neutral faces. These are whole brain analyses, but we particularly see that in the amygdala. And we don't see that in the control condition. So this is the responding in the intervention group and in the control group. So these behavioural changes map onto what we would predict to be the relevant neural changes as well. And so, of course, the interest is not just in terms of being able to measure individual differences in emotion recognition and their relationship to different psychiatric conditions, nor just in the ability to use the ability to modify those deficits and biases to understand causality, but also to potentially develop novel interventions that could be used adjunctively with CBT and pharmacological therapies. So thank you for listening. For your patience, I'd like to acknowledge the MRC in particular, who's funded much of this work, and the increasingly incorrectly named Tobacco and Alcohol Research Group. Thank you.